This is a long technical presentation that may not be for everyone, but I'll try to make it interesting even for casual viewers so that everybody can learn something new. Hi, I'm Linus, or LFT. I made a demo called Some Ergo Demonstro for the Raspberry Pi Pico 2 board with its RP2350 microcontroller. I'd like to take you on a tour of some of the inner workings of this demo. I won't go into every aspect, but rather focus on what I consider the most interesting bits from a technical point of view. And these bits are all very low level, very close to the metal. And they include two significant new discoveries or contributions to the field of RP2350 hacking. So welcome to the bleeding edge. I'll start with a brief overview of the various parts of the chip and how they work together in this demo. Then I'll present the first major contribution, which is my technique for layering effects in front of each other in a way that works with digital video and the HSTX peripheral. First, I'll explain how individual pixels are composited, then how they are assembled into Rasterlines, and then I'll talk a bit about a strange bug that caused the image to shake, so I dubbed it the Jitterbug. It's an entertaining mystery story, but also essential information if you want to experiment with this layering technique yourself. Then, as a bit of a palate cleanser, we'll dive into the RISC-V code for a small part of one of the demo effects. And finally, I'll explain how I used the Interpolator peripheral of the RP2350 to accelerate some 3D calculations. This is the second significant contribution to the field. So there's a progression from bird's eye view towards more details and more math, and you'll be forgiven for dropping off at some point if this goes way outside your mathematical comfort zone, but you'll try to push it a little, I'm sure. The RP2350 features two CPU cores, Core 0 and Core 1, and 520 kilobytes of RAM, organized as a main block of 512 kilobytes and two 4 kilobyte banks with dedicated bus interfaces. Program code is stored on an external flash chip, and since the flash interface is much slower than the rest of the system, there's a built-in cache to speed things up, but the RAM is accessed directly without a cache. Then there's a DMA subsystem supporting up to 16 memory transfers at a time. There's PWM for pulse width modulated outputs that I use for audio and for dimming the LED on the Pico 2 board. Speaking of audio, last year I made a demo for the RP2350 called Kaleidoscopico. That time I generated a VGA signal and analog audio. And this time I'm generating digital video but still analog audio. And several people have asked me why I didn't include the audio in the HDMI signal. And while there are some technicalities regarding HDMI versus DVI, the main reason is just that I decided to reuse my old audio implementation from Kaleidoscopico in order to focus my efforts on the video part this time around. Moving on, we have three programmable input-output blocks, PIO or PIO, of which I mainly use one for this demo. The PIO is a unique feature of the Raspberry Pi microcontrollers. It's versatile, quirky, and very useful. Helping out with digital video generation is the high-speed transmitter, or HSTX peripheral. And then, of course, there's a bunch of timers, interrupt controllers, and clock generators. The two 32-bit CPU cores are relatively powerful. They're rated at 150 MHz, and as mentioned, I run them in RISC-V mode. Just as in Kaleidoscopico, I've dedicated Core 1 to real-time functions closely coupled to video and audio generation, while Core 0 runs the actual demo effects, crunching numbers to produce pixels that Core 1 then puts together into a video signal. Core 0 fetches its instructions from the external flash via the cache, and the total size of that code is around 300 kilobytes for this demo. Meanwhile, Core 1 executes a single loop of code with one iteration per line of video, and the instructions for this loop are held in one of the RAM blocks with a dedicated bus interface. Since no other part of the system uses this memory block, Core 1 can always fetch its next instruction immediately and with fully predictable timing. In Kaleidoscopico, Core 1 would prepare and configure the PIO and DMA at the beginning of each raster line, and then spend the rest of the line computing one sample of audio using real-time FM synthesis. In this demo, for reasons that will become clear, Core 1 is involved throughout the video line, not just at the beginning, and that leaves too little processing time for running a real-time synth engine. Instead, the music in this demo is sample-based, and Core 1 only needs to mix 8 channels of sample-based audio into, again, one sample per raster line. This can be done in a fraction of the time compared to FM synthesis, But the downside is that all those sampled instruments occupy a lot of RAM. In my case, I set aside 64 kilobytes for sound samples. The video output runs at 31,500 Rasterlines per second, so that is also the audio sample rate. A bit less than CD quality, but still fairly good. The audio is converted into analog using pulse width modulation, as I mentioned, and I actually run the PWM at twice the sample rate, 63 kHz, and each calculated sample is emitted twice. This reduces noise by pushing the carrier wave well outside the audible spectrum, but at the cost of 1 bit of sample resolution. I get 12 bits of audio instead of 13. Now we turn to the video generation. This demo runs in a classic resolution of 640 by 480 pixels, so there are slightly more than 300,000 pixels on the screen. But if we were to put 300,000 true color pixels in a memory buffer, a frame buffer, even if we limit ourselves to 16 bits per pixel, then that buffer would have to be 600 kilobytes large. And of course, that doesn't fit in the available RAM on the chip. With a palette-based video mode, we could get away with 8 bits per pixel, making the frame buffer only half as big, 300 kilobytes, and so it would fit, but in practice, for most frame buffer-based demo effects you actually need 2 frame buffers in memory, a front buffer and a back buffer, and so again there's not enough RAM. But by switching to a lower resolution, say 320 by 240 pixels, and 1 byte per pixel, we get down to just 75 kilobytes per frame buffer, and then we can fit a front buffer and a back buffer and have plenty of RAM left for other purposes. And many effects look good in 320 by 240. In fact, many of the effects in this demo are running at this lower resolution and do use a pair of frame buffers, but they also have little high-resolution details like text overlays or silhouettes or this sharp black edge or the star. And so clearly, the physical video signal coming out of the demo board is 640 by 480, but it is made up of different layers, and some of those layers are running at 320 by 240. And those layers have to be upscaled and mixed with the high-resolution layers in real time while the video signal is being generated. I first implemented this kind of real-time video mixing in Kaleidoscopico for VGA, and I'll briefly describe how it was done there, and then build on that to explain why the same technique doesn't work for digital video on the RP2350. For VGA, you're continuously outputting 3 analog voltages that determine the red, green and blue color component. Every 40 nanoseconds, you change the voltages, thus clocking out new pixels at a steady rate. Then you've got additional sync signals to mark when a new row of pixels begins and when a new video frame begins. The RP2350, like most microcontrollers, doesn't have analog outputs, but you can wire up a bunch of digital outputs to a resistor network to produce an analog voltage. In Kaleidoscopico, I allocated 4 pins each for red, green and blue. So if we ignore the sync signals for now, all we have to do is set these 12 digital outputs to new values every 40 nanoseconds to build the video signal 1 pixel at a time. The PIO peripheral is tailor-made for this kind of job, where you have to update digital outputs with precise timing. It can receive a stream of pixel data from DMA and transfer those values one at a time to the output pins. In fact, the PIO contains 4 independently programmable state machines. Each of them has its own input queue for data, and each of them can control the output pins, either driving them to some desired value or not driving them at all. And if more than one state machine tries to drive the output pins at the same time, there's a built-in priority mechanism, whereby a higher numbered state machine overrides a lower numbered one. This priority mechanism is what makes the layered graphics in Kaleidoscopico possible. As I mentioned, there's not enough RAM to work with true color pixels. We need indexed modes, and sometimes even 8 bits per pixel is too costly. For Kaleidoscopico, I used 4-bit pixel values throughout the demo, and then I abused the instruction fetch mechanism of the PIO to map those values to 6 configurable colors per layer, and 1 additional value for transparent pixels. This is all described in more detail in my Kaleidoscopico write-up that you'll find linked in the video description. It's a slightly bizarre but ultimately useful approach, but it's very tightly tied to VGA. Because an HDMI-compatible video signal is an entirely different beast. Here you have 3 serial bit streams for red, green and blue respectively. Each bit stream is organized into 10-bit chunks that represent color intensities or sync information using an intricate encoding scheme that helps balance the electrical signal over time. Conveniently, the RP2350 has a peripheral called HSTX that can take care of the bit-level encoding for us. All that's left to do is to transmit a stream of true color pixel values and sync markers into the HSTX peripheral using DMA. And we don't even have to do this with precise timing, because the HSTX has a small input buffer, and as long as we keep the buffer topped up, the HSTX will handle all the timing for us. So that's great, but there's a problem. The HSTX doesn't have a priority mechanism. In fact, it doesn't support multiple data streams at all. You have to feed it one stream of the final pixels that will go on the screen. So to obtain several layers of graphics, we would like to have a way to combine the prioritized state machines of the PIO with the low-level bit encoding feature of the HSTX block. But the problem is that while the 4 PIO state machines can send data back out of the PIO using DMA, those output streams are per state machine. They are independent of each other and of the priority mechanism. The priority feature only affects what the state machines are putting out on the pins. So an idea comes to mind, which is to use the state machines to place pixel data on the pins, and then read the combined pixel data right back from the pins again. I did something like this many years ago in my demo Turbulence for the Propeller microcontroller. And the downside is that you can't put any external electronics on those pins, as doing so will interfere with the demo. But I found a better way to do it on the RP2350. In the very excellent datasheet for the chip, there's an entire chapter dedicated to the PIO, explaining its various modes of operation in great detail and with many illuminating examples, but one obscure feature isn't mentioned in the main text of that chapter. Instead, we have to scrutinize the reference list of hardware registers at the end of the chapter to find an absolute gem of a register called debug pad out. Read to sample the pad output values PIO is currently driving to the GPIOs. In other words, there's a debugging register that lets us peek at the output from the priority circuitry, the combined pixel value that would be emitted on the pins, but we can do this even if the PIO isn't routed to the pins. So in contrast to my Propeller demo, we can use those pins for something else and there's no interference. So now we can use the PIO to blend 4 layers of graphics to produce a precisely timed stream of composited pixels, just as in the VGA case. But instead of putting the composited pixels on GPIO pins, we pick them up in real time from this debugging register and pass them on to the HSTX. And we can work with up to 32 bits per pixel at no additional cost. But there's more. In Kaleidoscopico, all graphics were limited to 6 colors per layer in order to perform the palette lookup very efficiently inside the PIO itself. And while that was an interesting aesthetic constraint to work with, this time I wanted something more flexible. And since the pixel data is now leaving the PIO before reaching the pins, we can do things to the pixels in transit, such as performing color lookup from a much larger palette in RAM. So instead of outputting true color pixel values, the PIO can emit color numbers, or indices, into a palette. In fact, let's go even further and put complete 32-bit pointers to palette entries on the PIO output bus. The upper bits determine where in memory the palette array is located, and the lower bits select an individual element. This is particularly flexible because one state machine might fetch 8-bit pixel values used to look up one of 256 colors in a palette at one particular memory address, while the next layer state machine could use maybe 2 bits per pixel to index a 4-color palette at a different address in memory. Well, in practice a 3-color palette, because one bit combination would have to represent transparent pixels. Here's a simplified version of the PIO program for one of the state machines. We read in a number of bits, and yes, I know it's confusing that the instruction for reading input is called out. That's a PIO idiosyncrasy. Anyway, here we read 4 bits per pixel, but the program can be modified at runtime based on the desired graphics mode. Now, if all those 4 bits are 0, we jump to here and set a register called ISR, the input shift register, to 0. Then we delay for 1 clock cycle, and then we place that 0 on the pins. Except, as you know by now, the value doesn't end up on the actual pins of the chip, but in a debugging register in the PIO block. For any pixel value other than 0, we transfer a constant address prefix from register Y into ISR, and then we shift in the pixel value, pushing it into the low bits of ISR. Then we use the so-called program wrapping feature to get an implicit jump back for free, and then we output the combined value, the full address, to the palette entry. Both of these code paths execute in exactly 5 clock cycles per pixel. But look, the palettes contain 24-bit true color values padded to 32 bits, so the entries will be stored at word-aligned addresses in memory. That means we would have to push 2 more 0 bits into the shift register before we can move the ISR register to the pins, which seems to require 1 more instruction per pixel. However, here we can use the PIO pin mapping feature to say that the output from MOV pins should be relocated to start at pin 2 and continue for the full 32 bits, which makes the 2 most significant bits wrap around to pins 0 and 1, and this will be coming from the prefix in register Y, where we just ensure that they are 0. Now for another neat hack. As part of the configuration of a PIO state machine, you designate one of its output bits as the output enable signal. When this bit is 0, the state machine doesn't drive its outputs, and lower priority state machines can shine through. When it's 1, the state machine drives whatever output pins are mapped. Normally, the output enable signal isn't mapped to an actual GPIO pin. In Kaleidoscopical, for instance, the lower 12 bits of color values are mapped to the I/O pins for the VGA signal, and bit 15 acts as the output enable. But if you think outside the box, there's nothing in the specification that says you can't have one of the actual output bits double as the output enable signal too. And in this case I use bit 29 of the generated color address as the output enable. For pixel index 0, we emit the null value, which disables the output from this state machine, thereby creating a transparent pixel. For any other index, we emit the address of a palette entry in RAM, and on the RP2350, system RAM is mapped to an address range starting at hex 20 million, which means that bit 29 is always set. And because this bit also serves as the output enable signal, we get a solid pixel address on the bus. So that's how transparent pixels are implemented. A PIO state machine can also be configured to affect only some of the output pins, and thus to modify a part of the palette address emitted by a lower layer, while retaining the other bits, and that makes it possible to create various blending and translucency effects. And while we're looking at this effect, note how these layers consist of repeating patterns. Here I make use of another trick that relies on the ring buffer feature of the DMA controller. The tiles that make up these patterns all have widths that are a power of 2, and the pixels that make up the tiles are aligned in memory, so you can configure the DMA channel to read pixels from within the tile and then wrap around from the right edge of each line to the left edge. This allows you to save huge amounts of memory for horizontally repeating graphics, and that's why it's possible to have 4 simultaneous full-screen layers in this effect without running out of memory. So, to recap, this is a real-time approach where the video signal is generated on the fly, 1 pixel at a time, just as in VGA, but the signal doesn't go out on the external pins, but instead to an internal debugging register. And you can choose to emit new values from the PIO at a slower rate to obtain a lower horizontal resolution, and the pixel rate can be configured independently for each layer. The PIO is generating not colors, but addresses to colors, and for each pixel, we have to read the address from the debugging register and then perform a second read from that address in order to retrieve the actual color value from the palette and pass it on to the HSTX. This can be automated using DMA. You could set up a timer-driven DMA channel that reads from the PIO debugging register every 5 cycles and writes the value into a control register of a second DMA channel to trigger a copy from that address into the HSTX. And that will be a perfectly fine approach for applications where you want to leave both CPU cores free for other work. But I chose a different method. Between each raster line, in a digital video signal as well as VGA, is a horizontal blanking period, where no pixels are transmitted. This creates a bit of breathing room where you can take your time to prepare the PIO and DMA registers for each raster line independently. Therefore, it's straightforward to split the display vertically into bands with different properties. And this can be used to implement typical Amiga-style copper list effects, and is also useful for stretching low-resolution layers vertically. Each low-resolution line is simply emitted twice. Splitting the display also helps with conserving memory. You can have a small overlay like this, and some RAM is required to hold these pixels, but there is no need to store a large block of null bytes for these transparent areas. Instead, you simply don't enable that layer when preparing those raster lines. But what's going on in this screenshot? The Pio has 4 state machines producing 4 independent layers of graphics, but here we have 1, 2, 3, 4, 5 layers at the same time. How does that work? Well, in addition to vertical Amiga-style splitting, I also wanted to do horizontal splitting for this demo. So the 5th layer is not a layer as such, it can't contain individual transparent pixels. Instead, it's a distinct sub-rectangle of the screen, made from a vertical split and a horizontal split. But you can't really do horizontal splits in real time while the video signal is being generated, because there's not enough time to reprogram the Pio and DMA registers from one pixel to the next. A new pixel is emitted every 5 clock cycles, but it takes hundreds of clock cycles to reconfigure all the registers. So instead of transferring each pixel directly to the HSTX, I use what's called a scanline buffer. This is a block of RAM big enough to hold 1 Rasterlines worth of true color pixels, so in this case 640 words or 2.5 kilobytes. This buffer is in the other RAM bank that has a dedicated bus interface, because we need fast, undisturbed access to this memory. So during horizontal blanking, we configure the Pio and DMA registers to start generating pixels for the first horizontal segment of the upcoming raster line, and start putting those pixels into the scanline buffer. At some point, the horizontal blanking period will be over, and DMA will start transferring pixels from the scanline buffer to the HSTX peripheral. But we have a head start, and we'll make sure to generate pixels at least as fast as they're consumed. Now we get to the horizontal split, and here we stop generating new pixels and spend some time to reconfigure the system for the next horizontal segment. And meanwhile, the HSTX continues to consume pixels at a steady rate, so that when we're up and running again and emitting new pixel values, the head start has been diminished. And if you produce pixels at the same rate as they're consumed, then it turns out, based on the timing of the video signal and the performance of my code for setting up the registers, that there's enough time to configure the registers twice. That's once at the beginning of the raster line, and once more for a single horizontal split. But by overclocking the system, we can generate new pixels faster than they're consumed, and so while we're emitting pixels, the head start will gradually increase. That makes it possible to perform more than one horizontal split per raster line, as long as they're not all packed together near the left edge of the screen. Here's another example. The rotating star is confined to a small part of the screen, and I reconfigure the positioning of the splits to move the star around. So for each of these horizontal segments of the screen, all the Pio and DMA registers are reconfigured, but the lower layers are reconfigured in such a way that they keep reading from the same buffers without a visible seam. The topmost layer switches between displaying the star graphics and displaying nothing in order to conserve memory. But now the role of CPU Core 1 is to configure all the registers, then wait while pixels are generated, then configure the registers, then wait, and so on. Sometimes it has to wait for many pixels to be generated, perhaps an entire raster line, and sometimes it can be as little as a single pixel in a horizontal segment. This variability makes it impractical to use Core 1 for unrelated work while it's waiting. But on the other hand, I didn't want it to just sit and busy wait without doing anything useful. That is why I decided to not use DMA for the palette lookup, but instead perform that work using Core 1, because this is exactly the time where it would have been sitting idle, and this decision turned out to have a number of benefits. Here is a first attempt at some RISC-V code for performing the palette lookup. Recall that a new color address appears in the debugging register every 5 clock cycles. We load the color address from debug padout into A0, and then we perform the palette lookup by loading from that address into A1. This gives us a true color value that we store in the scanline buffer, and then we increment the scanline buffer pointer in register A3 and loop until we pass the end of the current horizontal segment. Some of you may have noticed that the add immediate instruction is missing an operand. It would typically read add I A3 A3 4. However, I made my own RISC-V assembler geared towards handwritten assembler programming, and it allows you to omit the first source operand when it's equal to the destination operand. Now we need to talk about bus collisions, because although Core 1 is executing code from a RAM block with its own dedicated bus interface, and although the scanline buffer is in the other RAM block with a dedicated bus interface, the palette is stored in the big common block of RAM that's also used by other parts of the system. Notably, Core 0 will be hitting that RAM all the time, as it's computing new pixels for the demo effects. and if both cores try to access the same RAM bank at the same time, they will have to take turns, which could slow down the system, but more importantly, mess with our real-time code. Luckily, the RP2350 has configurable bus priorities, and I've given Core 1 a higher priority than everything else in the system. As a consequence, whenever Core 1 tries to access main RAM, it is guaranteed to get through immediately in one clock cycle. Now, as you can see, we have 5 instructions per pixel, which seems like a perfect fit because the PIO program produces a new address in the debugging register every 5 clock cycles. But if you're familiar with the Hazard3 implementation of RISC-V, you'll see that this loop actually requires 6 clock cycles per iteration, because we used the value of A0 too soon after loading it, and this incurs a penalty of 1 cycle. This problem can be fixed by rearranging the instructions. Oh, and in case you're wondering, there's no similar penalty when we load a value and then immediately store it. This has to do with details of the Hazard3 pipeline implementation. But there's another optimization to consider, a very common and useful optimization technique on RISC-V in general. So let's go back to the original code. Loops on the RISC-V tend to follow this common pattern. There's some work to be done in each iteration, and then various pointers are incremented, and then there's a conditional branch. Now, because every memory access can have an offset added to the address for free, we can often unroll the loop and distribute the pointer incrementing and conditional branching across the unrolled iterations. Of course, you then have to account for the special case of a horizontal segment with an odd number of pixels, which involves entering the loop in the middle. So now we're down to 4 instructions per iteration, but again we have the penalty cycle because we try to use A0 too early, so the execution time is 5 cycles per pixel, which is exactly what we want. Given that Core 1 was just sitting around anyway, performance-wise this is no worse than using DMA for the palette lookups. But we can make a further improvement to actually beat that approach. Because every 5 clock cycles, a word of memory is copied from the palette in main RAM to the scanline buffer. And while we do this, Core 0 is probably in a tight loop calculating pixel values, and the performance of that code will now suffer due to bus collisions. These regular high-priority reads from the palette are blocking the bus for a small but significant proportion of the time. But we can recognize that very often the same pixel value will be displayed several times in succession. This happens in large areas of a single solid color, but also whenever low-resolution graphics are displayed, because a low-resolution pixel is essentially 2 copies of the same high-resolution pixel next to each other. Now, because we perform the palette lookup on a CPU core, we have the luxury of a fully equipped instruction set that can detect this very common situation and optimize for it. So we've got our unrolled loop, and there's no particular need to use the same register A0 in both halves of the loop, so let's use A5 in the second half. But now, in each half of the loop, we have access to the previous pixel color address in a register. So whenever A0 and A5 are equal, it means that the new pixel that we're going to output is identical to the previous pixel, and in that case, register A1 still contains the color value from the palette, and there's no need to load it again. So if A0 and A5 are the same, the branch is taken, a forward branch takes 2 cycles, and if they don't match, the branch is not taken, that's 1 cycle, and the load instruction is 1 cycle. So the total execution time is the same for both code paths. We're now back to 5 instructions per pixel, and it's possible to rearrange them to get rid of the penalty cycle. You might want to try that yourself as an exercise. But crucially, there's no longer a bus access to main memory when the same pixel is repeated. And for a low-resolution effect, this will be true for every other pixel, in which case we've just reduced the performance impact from shared bus accesses by a factor 2. But there's a really big problem with this implementation, and it took me a while to figure this one out. Because you see, I implemented this and it worked. The code on Core 1 was running with real-time priority, grabbing 1 high-resolution pixel from the PIO every 5 cycles like clockwork, and I was looking at a rock-solid display with both high-resolution and low-resolution layers, and I could place a horizontal split at any position I wanted, but there was only time for 1 horizontal split, remember, because I was generating pixels for the scanline buffer at the same rate as they were consumed. So my next step was to slightly overclock the CPU cores without changing the timing of the video signal. You can configure the HSTX to run from a separate clock generator, so this is not difficult, but when I did that, the image started to flicker towards the right side of the screen, suggesting that something was throwing off the timing of my real-time code. Because if core 1 is somehow occasionally delayed by a cycle, it will gradually drift out of sync with the PIO and start missing pixels. And if these delays are somewhat random, the timing will differ from one video frame to the next, leading to visible jittering. So I was pretty sure I was looking at intermittent delays, but I didn't understand why they were happening. And I experimented with different amounts of overclocking and discovered that if I ran the CPU cores twice as fast as in my original implementation, I would again get a rock-solid picture. But that meant running the cores at 252 MHz, when they are officially rated for a maximum of 150 MHz. As far as overclocking goes, that was a bit more intense than I had originally planned, but it seemed to work, and I knew that people had been overclocking RP microcontrollers quite a lot without any trouble, so since it made the problem go away, I decided to go ahead. And just like that, I was generating pixels exactly twice as fast as they were consumed. And I continued to work on my demo effects on Core 0, and I got to a point where I wanted to use one of the spare PIOs as a coprocessor for shifting some bits around. And suddenly there was the flickering again, somehow triggered by unrelated communication between two different parts of the system. Spooky action at a distance. And then I finally realized what was going on, or so I thought. When we give Core 1 a high bus priority, it gets precedence over any other part of the system that tries to access the same bus on the same clock cycle. But if there's already a transaction in progress on that bus, the ongoing transaction gets to complete first. For accesses to RAM, that's not a problem, because all transactions are single cycle, so there are no half-finished transactions. But on the peripheral buses, this is not guaranteed. And the PIOs and HSTX are connected to the same peripheral bus. Suppose a wait state is inserted there every time a new pixel is sent to the HSTX. Given that the HSTX runs in a separate clock domain, this is not an unreasonable assumption. And then, if Core 1 tries to read the debug padout register during that wait state, it will be delayed by one clock cycle. If pixels are generated by Core 1 at the same rate that pixels are transmitted to the HSTX, then the extra wait states can fit into the gaps between accesses to the debugging register. This also works when pixels are generated twice as fast. But for any non-integer clock ratio, at regular intervals there will be bus collisions, causing delays that make Core 1 drift out of sync with the PIO and start missing pixels. This is a perfectly reasonable explanation that matches the observed behavior. The only problem is that it's wrong. According to the datasheet, the HSTX does not insert wait states when you send pixels to it. That register has single-cycle write access from the DMA. The real explanation is much simpler. I couldn't have known it at the time because I relied on an older version of the datasheet, but there's a hardware bug in the chip, now duly documented as Erratum 27. And you won't believe this, some of the bus priority signals have been miswired. When we give Core 1 a high bus priority, that has the intended effect on the accesses to RAM for reading the pellet. But on the peripheral bus, due to this miswiring, Core 0 ends up with a high priority, leaving Core 1 and the DMA controller with a low priority. First of all, this fully explains the spooky action at a distance. If Core 0 has top priority on the peripheral bus and starts talking to a PIO, of course that will cause random delays in other parts of the system. But it also explains the original problem with non-integer clock ratios, and in much the same way as my previous theory. There will be regular bus collisions that keep delaying Core 1 until it starts to miss pixels. But now there's no need to invoke wait states to explain it, because Core 1 simply doesn't have priority, and every other time it has to wait for its turn to access the bus. At this point I was feeling rather frustrated, because sure, I could probably code a demo that didn't use any of the spare PIOs in a pinch, but my whole design was resting on a foundation of real-time guarantees from bus priorities, and that foundation had just vanished. Without those guarantees, my implementation was only working by accident. The fact that it sometimes didn't jitter was the bug. And here I could have reconsidered the DMA approach, because although a timer-controlled DMA channel would also see random delays due to bus collisions, those delays wouldn't pile up over time. But instead I decided to make the real-time code resilient to random delays. I still had to generate pixels faster than they were consumed, so I was going to keep the overclocking, the dedicated RAM blocks, and even the bus priority settings to ensure high performance. But I needed a system that could tolerate the occasional delay and wouldn't have to read a register exactly once every 5 cycles. And it turned out that this could be achieved in a quite elegant way at the cost of just 1 extra clock cycle per pixel, and that this actually simplified the PIO code. Remember the PIO code from earlier? To recap, we read pixel bits and concatenate them with a palette prefix and store that to the state machine output, except when it's 0, in which case we disable the output instead. Well, unfortunately, this is not the whole story, because this code snippet is only showing the high-resolution case, where a pixel is emitted every 5 cycles. For low resolution, the code is further instrumented with delays, and you also need a special case for when we start in the middle of a low-resolution pixel. See, we want to be able to move things around smoothly on the screen, so even low-resolution layers have to be positionable with high-resolution coordinates. The code to handle this is not difficult, but it's not particularly clean either. But now look what happens when we add one instruction to synchronize with the CPU. The PIOs have something called IRQ signals. IRQ is short for interrupt request, but that's a bit misleading in this case because nothing gets interrupted. Instead, the PIO state machine waits for IRQ signal number 1 to become 1, and this is something that we can trigger from the CPU. When that happens, execution in the PIO continues, and the IRQ flag is automatically reset back to 0. So this IRQ signal means the CPU has just consumed the previous output, please deliver the next one, which we then do immediately because we've already prepared it in the ISR register. If the IRQ flag was already set, the wait instruction completes in 1 cycle, so in the steady state we can now deliver 1 pixel every 6 clock cycles instead of 5, but crucially the CPU is allowed to be a bit late and we will adapt to that. The 4 state machines run different code and are programmed to respond to 4 different IRQ signals. This means that for low-resolution layers it is now the job of the CPU to request pixels at half the normal rate. From the point of view of the PIO, high resolution and low resolution now work exactly the same, and there's no need for a special case for starting in the middle of a pixel. So this code is very clean, but what does it look like on the CPU side? Well, here again is our unrolled loop that handles 2 pixels per iteration. And remember that there's a penalty cycle inserted after reading debug padout, because we try to use that register value immediately afterwards. In that delay slot, we now insert an additional instruction to set the IRQ flags for all 4 PIO state machines at the same time. This is done using the 4 lowest bits of a register called IRQ4s, so the value 1111 in binary is preloaded into register A6. Now we have 6 instructions per pixel and 6 clock cycles per pixel, so we're executing at the same nominal speed as the new PIO code. But now, if the CPU is delayed by an occasional random bus collision, the PIO holds back and remains in perfect sync. There's no need to use the same register A6 in both halves of the loop, so let's use A7 in the second half. And there's no need to have all 4 bits set in both of these registers. Instead, for a low-resolution layer, only one of registers A6 and A7 will have a 1 in the corresponding position, so a new pixel will only be requested from that layer every other time that debug padout has been sampled. And which one of A6 and A7 has the bit set determines whether we start with a full-size or half-size low-resolution pixel. So, in conclusion, unrolling the loop to handle 2 pixels per iteration serves 3 independent purposes. It optimizes the RISC-V code by distributing the increment and compare instructions. It lets us reduce bus traffic by having the previous pixel value available in a register. And it simplifies the handling of low-resolution layers. This concludes my presentation of HSTX-compatible layered graphics. And now for something completely different. So far, we've seen RISC-V code for moving data around and basic logic like comparing and jumping. I thought we should also look at a small routine that actually computes some numbers, and does so using slightly more exotic opcodes. RISC-V is a modular architecture, and various implementations of the RISC-V standard may or may not include a number of optional instructions. And I think that the configuration chosen for the RP2350 is good and balanced on the whole. It includes some esoteric but useful instructions while not being bloated. The code I have in mind is running on core 0 as part of this effect. The greetings are displayed in their own high-resolution layer, modifying 2 bits per pixel using the translucency technique that I mentioned earlier, and this text layer is redrawn from scratch on every video frame. Behind that is the interesting part, and this effect is called a fractal flame. We're looking at a low-resolution layer with 8 bits per pixel, and this layer is not redrawn all the time. Instead, it accumulates data from one video frame to the next. Fractal flame is an iterative algorithm that can create stunning pictures in high resolution and at least interesting and varied pictures in the more modest display mode we're using here. The algorithm itself is well documented elsewhere. I'll leave a link in the video description, but essentially you iterate a formula to hop from pixel to pixel, and every time you land somewhere, you increment a counter for that pixel, increasing its brightness a little bit. Here I can manage about 50,000 iterations per frame, and so when you see each new picture appear, you're looking at the actual gradual computation of the fractal flame. So you've got these counters, one for each pixel on the screen, and the counters have to be at least 16 bits wide. But a 16-bit video mode would be impractical because the palette would have to be absolutely huge. So at some point in the effect code, we have to convert a 16-bit counter value into an 8-bit pixel value. But an interesting property of the fractal flame algorithm is that the brightness of the color you display has to be proportional to the logarithm of the counter value. This creates a kind of 3D illusion. Without the logarithm, we see a flat mix of all the different paths that the algorithm is tracing out. With it, we no longer see the paths less traveled by, and that makes all the difference. A trivial way to implement this logarithmic transform would be to use the upper 8 bits of each 16-bit counter as they are, as the pixel value, and then incorporate the log function into the palette. The palette is pre-computed at build time, so there we can use complicated math at no cost. But the problem with this approach is that we get a very jagged palette with big leaps between adjacent colors. So we could really benefit from approximating the log of an unsigned 16-bit value with an 8-bit value, and this is where we can use some specialized RISC-V instructions. First, we're going to take our 16-bit value and count the number of leading 0 bits. We've just incremented the counter and have the new value in A0. And because we just incremented it, we know it's not 0, so the number of leading 0 bits will be from 16 to 31 inclusive. Well, technically it can be 15 if the counter just overflowed, but we'll ignore that case. And this is already a good first approximation of the logarithm, but it's very coarse, with only 16 possible values. So next we'll want to look at the most significant bits following the leading zeros. So we move those bits to a known position by shifting left by the number of leading zeros. Now A0 has this shape. The most significant bit is always 1, and then we have some varying bits coming from the original value, and then a lot of zeros that were shifted in at the bottom. And we want to look at the most significant of those X bits. So we use the instruction bit extract multiple immediate to take 3 bits starting at bit 28 of register A0 and put the result into register A2. We still have the number of leading 0 bits in A1, and 3 significant bits of the original value in A2. These can be thought of as the exponent and mantissa of a tiny floating point number, and the final step is to pack them into a single 8-bit color index. For that, I used an instruction called shift3add, which is mostly intended for pointer arithmetic, but here I found another use for it. The result is a byte with bit 7 set, then a rough approximation of the log in 16 possible levels, and then a subdivision of that level into 8 possible substeps. This means we're wasting 1 bit in the encoding space, and the effect will be displayed with 128 rather than 256 colors. Why? Well, if there had been a shift4add instruction on this processor, I would have used it to obtain the full 8-bit color resolution. But shifting by 4 and adding using separate instructions would have made the code a little bit slower, resulting in fewer fractal flame iterations per video frame. This kind of trade-off is common in demo coding, and you simply go with the option that looks best. In this case, I felt it was the faster version with fewer colors. When we generate the palette at build time, we work backwards from the bit fields in the color index. We figure out what 16-bit value could have resulted in the given bit combination, and let the logarithm of that determine the brightness of the corresponding palette entry. And then, instead of this, we get this. Not bad for just 4 instructions. We've covered video signal generation and some highly specific RISC-V code. Now I want to talk about another peripheral that's specific to the RP series of microcontrollers. A peripheral that's peculiar, but also very useful once you wrap your head around it. And that's the interpolator. This strange little coprocessor has several modes of operation, and the one I use in this demo works as follows. Each interpolator has 2 32-bit accumulator registers and 3 32-bit base registers. Every time you read the interpolator output, 2 things happen in a single clock cycle. You read out the sum of base 2 and the accumulator registers, but the accumulators are rotated and masked according to configuration settings. That means you can, for instance, have a pointer to a 2-dimensional array, like a texture, in base 2, and then you rotate and mask to get the upper bits of accumulator 1 into the row index of the 2D array, and the upper bits of accumulator 0 into the column index. This way you get a complete address to a byte in the texture that you can then read from using the CPU. The second thing that happens in the same clock cycle is that the base 0 and base 1 registers are added into the corresponding accumulator registers. The accumulators work like fixed point numbers, and with every access they are incremented by a constant amount. As a result, we step through the texture independently in the x direction and the y direction, and that's very useful for implementing, say, a roto-zoomer. Each CPU core has 2 dedicated interpolators, and now I'm going to show you how I used the interpolators of core 0 to accelerate rasterized 3D graphics. This won't be a comprehensive tutorial on 3D graphics, you can find plenty of those online, and I want to focus on how I used the interpolator in a new and spectacular way. But in order for that to make sense at all, I think I should briefly cover some general terms and concepts. To render something like this, you start with a 3D model, which is a set of triangles in 3-dimensional space. Then you use math to project those triangles onto a flat surface, so you end up with a bunch of 2-dimensional triangles to draw on the screen. Each corner, each vertex, now has a position on the screen in x and y pixel coordinates. And it can also have other properties like color or texture coordinates. We'll use color in this example. To draw such a triangle on the screen, you have to update all the pixels inside it. And if the vertices have properties, you need to interpolate between those 3 values based on where you are in the triangle. And this interpolation needs to be done right, so that, for instance, along this edge, you only get shades between blue and green, but no red at all. And the proper way to do it is to use something called barycentric coordinates. For any given point P of the triangle, imagine that you subdivide the triangle like this. Now, this area divided by the area of the whole triangle tells you how much of this color, or texture coordinate or what have you, to blend into the final mix. This area divided by the whole tells how much of this color to use. This area divided by the whole tells you how much of this color to include. These 3 proportions are called the barycentric coordinates of the point, and their sum is always 1. And from this geometric definition, you can now derive a formula for the barycentric coordinates of any point given its x and y coordinates and the coordinates of the 3 vertices. Without going into the details, this is the formula you get for the first coordinate, this is for the second coordinate, and once you have those, you can trivially compute the third barycentric coordinate, since we know they add up to 1. The big thing to note about these formulas is that they are linear with respect to px and py. When we move from one pixel on the screen to the next, either down or across, each barycentric coordinate will change by a constant amount. In other words, if we step through the pixels of the triangle systematically, one line at a time, we can track the changes to the barycentric coordinates using the hardware interpolator. And since the plan is to use the barycentric coordinates as weights for mixing properties of the vertices, we can even pre-multiply those properties into the base and accumulator values. Since each interpolator has 2 accumulators, we can handle a pair of texture coordinates, for instance, using a single interpolator. So this setup is identical to the roto-zoomer example from earlier. The only difference is that we now use barycentric coordinates to compute the initial parameters that determine the amount of zoom, rotation, and skewing. But what I'm about to show you now does not involve any vertex properties. we'll be using one of the interpolators to compute raw barycentric coordinates, because you see I rushed past something. In order to visit every pixel of a triangle, we first have to determine which pixels belong to the triangle and which don't, and that's a non-trivial problem in its own right. So remember how we defined barycentric coordinates using ratios of areas, and then used geometry to derive formulas for the weight of each vertex. In doing so, we assumed that the point P would be located inside the triangle, and the formulas would then always give us 3 sensible weights. But in the kind of mind-bending plot twist that only math can deliver, it turns out that if we put into these formulas the coordinates of a point outside the triangle, then at least one of the barycentric coordinates will end up negative. And this is great, because now we have a simple way to test if a pixel is inside or outside the triangle. So here's what we do, and this is not the only way to draw triangles on a screen, but it's one common technique. From the vertex coordinates, we can easily compute the minimum and maximum x and y, and this gives us a bounding box. Then we compute the barycentric coordinates a, b, and c for the top left corner of the bounding box using the formulas. Typically this will be outside the triangle, so one or more of the coordinates will be negative, but that's fine. We also compute how much a, b, and c change when we go 1 pixel to the right and when we go 1 pixel down. And then we just iterate over every pixel in the bounding box, 1 line at a time, and update the barycentric coordinates as we go to determine if the current pixel is inside the triangle or not. And obviously, for some degenerate cases, iterating over the entire bounding box is inefficient, but in practice, when you have lots of small triangles, it works quite well. So as we're visiting every pixel of the bounding box, we'll be using one of the interpolators to track a and b as fixed point numbers. For every pixel, we could read out a and b separately from the interpolator and compute c as 1 minus a minus b, and check if either of them is negative. If so, we're outside the triangle and skip that pixel, otherwise we draw it. Meanwhile, we can use the other interpolator to track color or texture coordinates. But now we get to the spectacular part. And to my knowledge, this is a new discovery and thus the second major contribution in this video. See, I figured out a way to check for a negative a, b, or c instantly using the logic of the interpolator itself. So again, we track a and b as fixed point numbers using the 2 accumulators. They can be positive or negative, but we can ensure that they are in some bounded sensible range. In my case, I used 16.16 fixed point, so inside the triangle, a and b would be in the range 0 to 2 to the power of 16, but they can also venture quite far outside this range without any risk of overflowing the signed 32-bit range. Therefore, if we instruct the interpolator to mask away the top 2 bits of both values, keeping only bits 0 through 29, then any a and b coordinates corresponding to pixels inside the triangle will be non-negative and preserved as they were, but negative numbers will turn into very large positive numbers. Meanwhile, we keep the base 2 register at a constant -1, or minus 2 to the power of 16 in fixed point. Recall that the output from the interpolator is the sum of base 2 and the accumulators after masking. If the first barycentric coordinate a is a negative number, then the masking will transform it into a large positive number, and the output from the interpolator will be positive. Likewise, if b is a negative number, the output will be positive. But if neither a nor b is negative, then the masking preserves their actual values, and the output from the interpolator is equal to a plus b minus 1, which by definition is minus c, the third barycentric coordinate with inverted sign. So now if c was negative, the output is strictly positive, otherwise it's not. So in every possible case, the output from the interpolator is greater than 0 if and only if at least one barycentric coordinate is negative, which is exactly the condition we want to check. And so in the code, where we iterate over the pixels of the bounding box, the entire triangle check boils down to this. We always read from both interpolators because we have to advance the texture coordinates even if we don't need them for this particular pixel. But if we tried to use A0 immediately after loading it, we would incur a penalty cycle, so arguably we get to advance the second interpolator for free. And then we just branch to skip the pixel if the output from the first interpolator was greater than 0. And that's how I used the RP2350 interpolators to accelerate 3D graphics in my demo. and how I combined the PIO priority circuitry with palette lookups and HSTX-based digital video generation. Now go and make your own discoveries, because this chip is not nearly fully mapped out yet. Thanks for watching all the way, take care, and I'll see you in the next one.